All right, so if you can easily understand my funny English, then you have definitely seen too many Arnold Schwarzenegger movies. But the story with the flying cow is actually correct. It really was unfortunate cow that lost its footing on a steep hillside in Nepal and came crashing down and just missed me by like a meter or 3 feet. All right, so but tonight I don't want to talk about flying cows. I want to tell you about a planet that I helped discover this year, and some of you, last year actually. So it was kind of in the news in summer 2016, so you might have heard already about this. And let's tell you a little bit about how you probably can follow this presentation. The planet's official name is a boring Proxima b. And whenever I utter this phrase, you have to take a sip from your drink, a good sip, okay? And I will do the same. So that's the first important rule to really follow this talk properly. The second rule is, if you see the famous ATX Astronomy on Tap icon somewhere in my slides hidden, you also have to do the very same. You take another sip from your drink. I hope everybody has drinks, right? I won't follow the second rule because otherwise this presentation gets very quickly very incomprehensible. So where can we see Proxima Centauri? Where do we need to look to see this star? Proxima Centauri, of course, is the nearest star to the Sun. It's just a meager 4.2 light years away, just around the corner. Basically our galactic backyard. But where do you have to look? Well, you have to look like right over there. Unfortunately, it's in the southern hemisphere. You cannot see it from Austin. Even if it would be clear, we wouldn't see it. And it's very close to its much brighter companion star, the famous Alpha Centauri. And Proxima Centauri is right there. It's hard to see. And the funny thing is, you wouldn't even be able to see it at all with your naked eyes. It's so faint, it's such a small star that it's invisible to our eyes. It's way beyond the kind of detection limit of our eyes. But it's an interesting star, not only because it is the closest star to the Sun. It's a very small star. It only has about 12% of the Sun's mass, so it's like a very low mass star, as we say. At the very end, where stars still manage to do nuclear fusion and produce energy to send light out. But what is really interesting about a star like this is that if you have a low mass star like this, you can actually detect planets, very low mass and very small planets, with current technology. And I'm gonna tell you the story how we found Proxima b. How far is 4.2 light years? Well, it's still very far. So to give you an idea, there is a very nice kind of scale model that you can use for thinking. If you would reduce the Sun to the size of a tennis ball, the Earth would be just a little dust corn about 19 feet away from the Sun, from the tennis ball. The 4.2 light years to our Proxima Centauri would be about 900 miles. And that's the nearest star to the Sun. So obviously space is really big. This is one of my favorite quotes from Douglas Adams. And even though this is the closest star to the Sun, we could not just point a telescope at it and snap a picture and see a planet. No, that would be way too easy. It's so far away that even nowadays, it's incredibly difficult to image planets, even around the nearest stars, because they're still so far away that the planets appear very close to their host stars. And so they're basically overwhelmed by the billion times brighter light source. That's the major problem. But we astronomers can use indirect methods. And the indirect method that was used to discover Proxima b double. Is called the radial velocity technique, which is kind of boring astronomical lingo. It's commonly known as the wobble technique. And what we exploit with this technique is basically that the planet has a tiny amount of mass, even compared to the star, and that the center of mass of a system like this, of a star and a planet, which is shown in this kind of animation as the green cross, is a little bit displaced from the center of the star. The same happens to our sun. So if an alien astronomer would observe our sun very, very carefully, even if that alien astronomer wouldn't have the capability to find the planets, it would see the motion of the sun due to the unseen orbiting planets. And again, this is actually not how we find them. What we actually are doing is we are using a technique that's called spectroscopy, which is splitting up the starlight into its colors. And you probably have heard of the Doppler effect. The Doppler effect is the same effect that the police officer is using when they measure your velocity on 183 or I-35 and maybe end up giving you a speeding ticket. Anything that is, when the source of the wave is moving towards you, everything gets shifted to higher frequencies, or when it comes to light, to bluer wavelengths. And the same is true, or the opposite is true for the other effect. So if the source is moving away from you, the light gets redshifted. And for these tiny motions of a star around the common center of mass with an unseen planet, these motions are very, very small and slow. So we have to measure these velocities of these stars very, very, very precisely. We basically have to measure them at the level of about 1 meter a second, which is kind of like fast walking speed. So how did Proxima come into play? When I was finishing my PhD at the European Southern Observatory, this observatory just built their newest, coolest, biggest telescope, which was called the VLT, which stands for Very Large Telescope, which was 8 meters in diameter. And it had an instrument that allowed us to do this Doppler velocity measurements very precisely. So my thesis advisor and I, we sat down and we were like throwing ideas around, what can we do with this big telescope now? And obviously was, okay, why don't we look now at these stars that were way too faint originally to use this technique on? And even better, because these stars were so faint, like Proxima, they're so low mass that even with the velocity precision that we could measure, we would be able to detect Earth mass planets, which was completely unheard of in the year 2000. The field of exoplanets moves so fast that nowadays we have like thousands of Earth-sized or small planets, mostly coming from NASA's Kepler mission. But back in 2000, we had a handful of Jupiter-sized planets. So we started to monitor Proxima Centauri. And here's actually our data here. So this is time, and this is velocity. So you see there's not much going on. So we immediately realized there are no giant planets orbiting Proxima. We would have seen that easily. And I actually took these data to kind of estimate which planets can we already rule out, just looking at these measurements. And it was 2 to 3 Earth masses in the habitable zone of the planet, of the star. So we said, okay, that's pretty good. And we moved on to other projects. Plus, at the same time, around 2007, a new instrument at the same observatory became available, which was also used to look at Proxima Centauri. And they observed, it was our friends from the Geneva Observatory, they observed with this new instrument, Proxima Centauri, for the next 7 years, and also found nothing. But what happened then was that somebody did kind of the obvious. Guillaume Anglada-Escudé and his friend Mikko Tuomi, they just took all the available data, so our old data and the new data, combined it, and what they found was kind of an interesting signal. So what you see here, this figure here, shows you as a function of periods, so these are orbital periods of possible planets. And this here shows you how likely there is a true signal in the data, and more importantly, here's the true ATX Beer scale. So even though there was an interesting peak at around 11.2 days, they were not sure, or we were at that point not sure that this is a true signal. So what happened next? Well, what's usually happening in science? You design an experiment to very efficiently, very quickly falsify or confirm whether this is a true signal or just a false signal, a false alarm. And that came to be known as the Pale Red Dot campaign. Guillaume was able to persuade the European Southern Observatory to give us time at this telescope. Did everybody get that? I don't see many people taking sips. To observe Proxima Centauri every night, they're able to open the dome for 60 consecutive nights. And this is the data. And the blue line that kind of shows nicely that 11.2 day signal shows up incredibly well characterized in these new data. And that's how Proxima b was actually detected. So these are the same kind of Beer likelihood statistics. Here we have the original, what I've shown you earlier, not really super significant. This is the signal just taking those 60 nights alone. And exactly at 11.2 days, you have this very strong peak. But what convinced all of us and most of the astronomical community, and hopefully you guys too tonight, is if you look at this Beer statistic, there's an incredibly strong signal now if you combine all the available data, which shows you also that that signal was present in all our measurements going back all the way to the year 2000. So it was 16 years of these precise Doppler velocity measurements of this particular star that led to the discovery of a planet at an orbital period of 11.2 days. And because the amplitude of the signal was so low, the planet has an estimated mass of somewhere between 1.3 and 3 Earth masses. So this planet is known as Proxima b. And it's kind of in a weird orbit and in a weird location, especially compared to our solar system. So here on the left-hand side, you have our solar system, the Sun. Then on the right-hand side, you have the Proxima Centauri system. There's Proxima Centauri, which is so much smaller than our Sun. It's barely bigger than our planet Jupiter. Its luminosity is just about a 1,000th of our Sun's luminosity, meaning if you want to have a planet warmed to the same degree as our Earth is, you have to move it very close in. So unlike in our solar system, where the habitable zone is around 1 year orbital period, the orbital periods of habitable zone planets around Proxima are just a few days to 2 weeks. So our 11.2 day planet is just right there in the habitable zone. And that was, of course, very exciting, because now we have a planet that orbits the nearest star to the sun and is even possibly an Earth-like planet, a rocky planet with an atmosphere and with the possibly the right temperature to have liquid surface water. And where you have water, you have, of course, the possibility of little aliens. So what are we gonna do now after we now know that even the nearest star to the sun has a potentially habitable planet? Oh, by the way, of course, we have already a first picture from the surface of this planet. Don't ask me how we got it. But it's very interesting that if you envision to stand on the surface of this planet, Proxima Centauri would be 3 times bigger, despite that it's so small, than our sun in our sky, because you're so much closer. And even during daylight, you would see Alpha Centauri A and B as a very bright double star in the daylight sky. And this is, of course, the hypothetical surface of Proxima b. Just checking. We don't know. We, of course, don't really know that the surface looks like this. Under best circumstances, the mass is low enough that it's a rocky planet similar to the Earth, at the right distance, having an atmosphere, possibly allowing, therefore, liquid surface water. But what can astronomers do? So it was not only the public that got really excited last year when this was announced. It was also the astronomical community, in particular the exoplanet community, because they jumped on this because now we finally have a target that's so nearby that we can use future instruments and telescopes, like maybe the James Webb Space Telescope, the Giant Magellan Telescope, or the Europeans are even crazier. They're going to build an even bigger one, the extremely large European. No, the European Extremely Large Telescope. To take spectra of this planet and detect signatures of possibly biosignatures in its atmosphere. I think Dan is going to talk about this a little bit more. But you can even think a step further. Why don't we go there? It's just around the corner. It's 4.2 light years away. So how long would it really take us? So the fastest human being, Usain Bolt, everybody knows that, he would run about 100 million years. It probably gets tired on its way. One of the fastest animals is the cheetah. Even a cheetah would run 38 million years. Our fastest car takes us there in about 3 million years. It gets much, much better. The Concorde would do it in 2 million years. Our fastest moving spacecraft currently is the New Horizons probe that was launched to fly by Pluto. It would take about 80,000 years. It's not going there, but if it would be targeting Proxima, it would take 80,000 years to get there. So that's still pretty long. And we all know, of course, that the Millennium Falcon just takes under 12 parsec to get there. But as crazy as it sounds, people are actually working on this. In April last year, I was invited to go to Stanford for a workshop where the breakthrough Starshot project was discussed. And it's a guy like Yuri Milner is one of these Silicon Valley billionaires. But this guy you probably also know. They are on the board of this project. And the idea would be to actually make a probe so small that you can attach it to a light sail and then hit it with a gigawatt laser for just a few minutes. And they ran the numbers and they said that would accelerate it to 20% the speed of light, which would get you to Proxima Centauri in about 20 years, which still sounds long, but you must remember that our solar system exploration was of similar timescales with the ordinary probes. Of course, there are interesting facts associated with this, or political issues. I mean, this is like right out of a James Bond movie. I don't know how we will ever solve this issue that somebody has control of a several gigawatt laser array somewhere on this planet. But that's the idea. And of course, if you can send a probe there, you can take direct measurements possibly of the magnetic field, take pictures, crude pictures, with a few pixels resolution, see maybe continents, clouds, blah, blah, blah. The little aliens, hopefully. And that's it. Thank you very much.
All right, Proxima Endl, thank you so much. All right, I'm sure there's going to be some wonderful questions here. All right, we're going to go from the back first, up at the top. Shout it out.
Yes. So the question was, using the wobble technique, we have one certain limitation. We don't know how the planetary, the orbit of the planet, the plane in which this planet orbits, is inclined to us. Meaning we could look totally perpendicular to the orbital plane, meaning it orbits just like this. Then we wouldn't see any Doppler shift at all, and there could be a supermassive planet around that star, and we wouldn't see it with this technique, because the star still has to move towards and away from us. Only when we are in the fortunate case that we look precisely into the plane of the orbit, so the tilt is 90 degrees, then we would measure directly the true mass of the planet, and also the planet would transit in front of the host star. So that's why you have to play some kind of statistical game at this point. What we really measure is we don't know this inclination of the orbital plane, so we measure only a minimum mass, which is this 1.3 Earth masses, which only would be the true mass if we would have 90-degree viewing angle. But then you can go run the numbers of how likely are orbital planes inclined like this. Unfortunately for us, that it's completely perpendicular to us is the most unlikely scenario. So that's why I said the planet has very likely a mass between 1.3 and 3 Earth masses, because that's the 90% probability range.
Okay, saw this gentleman first.
Do we have any evidence that the orbital planes of these planets are randomly distributed, or are they preferentially similar to the galactic orbital planes?
Excellent question again. No, there is no evidence that there is any preferred orientation of orbital planes for planets, nor binary stars in the galaxy.
Okay, right up here up front.
Why is it Proxima B? Was there a Proxima?
Well, that's just nomenclature kind of adopted from binary stars. At the very beginning, when astronomers realized that one single star that they thought was single has actually a companion star, they would label the primary star, the more massive, more brighter star, A, capital A, and the less massive, maybe new discovered star, capital B. Now with planets, we did the same thing. We called them basically according to the name of the star. But then, since it's not a star but a planet, we call the first planet that we discover lowercase b. That's why it's called
Proxima B.
Thank you.
Okay. All right, in the back of the... Yep, you, sir.
I should click this.
You showed a couple examples of some of the new telescopes that are going to be online in the coming years. Will any of them actually be powerful enough to directly image a planet like Proxima B?
Yes. So interestingly, so the question was, is any of those new, newly available coming? No, stop. See, this was too much. So these big telescopes that will become available, they are powerful enough to directly image. In particular, the Giant Magellan Telescope will be the ideal instrument with a very powerful imaging system that will be able to directly image Proxima b. The James Webb Space Telescope will not be able to directly image it.
And you might want to make sure you stick around for the third talk. We're going to be talking a little bit about that as well. All right, our last question, we're going to go right here to this young gentleman right there.
How long would it take you to find, let's say, Earth out of, let's say, you get 10 stars?
So you're asking if I would be an alien astronomer 10 light years away from the sun, and how long would it take me to find Earth? Forever, at the moment. Only if I have better technology than we have nowadays. Well, not really. If for instance, NASA's Kepler mission was designed to do exactly this. And Kepler can do this for stars that are way, way, way more distant than 10 light years. So if an alien astronomer would build a Kepler mission, and it would be just by chance lying in the orbital plane of the Earth, so that it would see the Earth crossing in front of the sun, you would be able to see the Earth, at least determine its size as a planet and orbital period, from hundreds and hundreds of light years away.
Okay, well, I'll follow up.
If somebody does do that, actually, when you saw Alpha Centauri and then you had that peak at 11.2 days when Proxima B crossed.
Yeah.
Would somebody get stuck?
You guys are slacking. Yes, exactly. So, and that's also a very good question, but why is this more difficult? It's more difficult because the sun is way more massive. It's more than 10 times more massive than Proxima Centauri. And the Earth is also much further away than this planet. Orbits with, well, as you know, 365 days. So these Doppler velocity measurements, the amplitude of this signal, the strength of the signal is depending on how massive the star is, how massive the planet is, and how far the planet is. So our Earth induces on our sun only a velocity variation of plus minus 9 centimeters a second. And this is currently beyond our capability. But we're working on it.
All right, let's thank Proxima Endl one more time.